Okay, good. So today, last time you guys saw backpropagation. So you saw the value of momentum and specification of the gradients, approximate gradient computation. So the lecture with Edwin should have covered those things. So today we discuss a little bit regularization. So the regularization is used mostly in terms of driving the optimization away from bad local optima. And this is an example of of a bad function, right? Because you see that this is a hyperbolic paraboloid. Just a difficult word to say this. This is a function which is convex on one variable and concave on the other variable. So you can imagine that if you traverse, if you perform SGD along this direction, you will find this as being the minimum of the function. But of course, as a minimum, this is an unstable minimum because if you have to take some other direction, then you will proceed further down along some other direction. Okay, so basically we want to regularize the process of learning so that we can, let's say, stay away from bad local minimal and unstable local minima. And this is generally referred to as regularization. And regularization, it's a general term which says that any modification that is made to a learning algorithm that is intended to reduce the generalization error, but not the training error. Okay, so remember that we always have this this balance, right? So one is the generalization error, which is how well does the network perform on seen data. And then, so like how much the network learns the pattern inherent in the data. And then we have the training error, which is the error that actually you see when you perform training. Okay. So let's go from the from the easy to the hard, let's say, from the easy to the harder forms of the regularization. So first of all, one is norm penalty. Okay. So we all know that the enemy that we are always fighting is overfitting, right? So here you see an example that was also in one of your challenges, right? So here there is the function x sin x, and here there is the prediction to the neural network. And then you see that in the training set, you provide the function with some additional noise. In the validation, you also have the function with some additional noise. So the idea is that if you see the blue observations of the training set, and you let the network train for a long time, then what the network does, it tries to catch, let's say, to fit not only the pattern in the data, but the data point itself. And in this case, it tries to interpolate the noisy point, the noisy evaluation of the sine function. Sorry, guys, I just, there is a storm going on that just started, and yeah, so it's, the light dropped, and it's a little bit scary. No, not scary. It's a little bit of a dramatic weather change for me. Okay, good. So the idea is that in general, what we do is that we want to minimize a certain loss, right? So the loss is with respect to the weights of the network, given the input and the output level. Okay, so you want to change the objective of this optimization to add an additional term, which is alpha times omega times weight, omega of weights. So you interpret this as follows. Alpha is what you will call a Lagrangian. So the term comes from optimization theory. And basically, the alpha term, let's say it goes between 0 and 100, it weights the penalty term, the regularization term, versus the loss term. This will be clear in a second. And that's this omega function. So omega is a function, and crucially, it's a function only of the weights. And what type of functions are we interested in considering? For example, omega as being the L2 norm, or omega as being the L1 norm. Okay, so the idea is that we want to take our minimization of the loss function with respect to the weights evaluated over the data set, and we want to add another penalty term which only consider the weights. And for example, we want to penalize, right, the network having large weights. And what type of penalty function we choose? We can choose the L1 norm or the L2 norm. Okay, so this is not immediately intuitive to you, as of why, for example, there is any difference choosing this function versus this function. Okay, but once you play around with learning for a long time, then you learn the different values of the choice of the penalty function. So for example, in the L2 regularization, right? So if we penalize the L2 norm or the weights, this will have a good effect on the type of problem where you're doing some sort of maximal posterior estimation with Gaussian priors, right? So if there is an idea that the weight the weights should behave in some sort of Gaussian manner, right? The weights should have some sort of Gaussian distribution, then you usually use an L2 norm. Whether if you use an L1 norm, effectively what you're doing is that you are trying to push weights to be exactly zero instead of being small in let's say an L2 norm. And there's a very fine discussion as of why L1 norm has this effect. And this, for example, is good if you're doing some sort of a Laplacian prior, right? So the Laplacian function is 1 over e to the minus absolute value of x, right? So the idea is that now we are measuring the distance between points in an L1 norm. Okay, so this is this type of regularization. They really need to be designed according to the problem that you have at hand and what type of understanding you have of the data, right? So the idea is as follows, right? When we run backpropagation, we want to do the same as before. So I want to update the weights according to the derivative of the loss function with respect to the weights. And now what we're doing is that we are adding a term, and this term only depends on the weight. So when we take the derivative, this derivative does not involve the data set, right? And so basically what happens here is that, for example, when you have your weight updates, you update the weights to go in the negative direction of the gradients plus, right, this term here, which is simply decreasing the average magnitude of the weights, right? You see that here, you can collect this term and you have omega I, multiplied by 1 minus lambda alpha. So let's just call this C as a constant. So you see that your weight updates are always the current weights multiplied by a constant which is less than 1. So this will correspond to an exponential decay of the weights, okay? Because you keep multiplying at each iteration the current weight by 0.9, let's say. So the first iteration you multiply by 0.9, the second iteration will be 0.9 squared. So this effect is sort of exponential. Of course, if there is no gradient. And this is usually called decay of the weights. Okay, so you tend to choose the weights so that their average magnitude is always decreasing. Okay, and the reason why you want to do this, of course, is because you want networks that have smaller weights, because networks with smaller weights have more predictable behavior, and so they tend to avoid large, let's say, large change of outputs on unseen data. So this L2 regularization or this L1 regularization has the meaning of making your network less erratic in its behavior. And you see here that the effect is to avoid the interpolation of these outlier points, right? And you see that the network behaves in a smoother way. And there is a qualitative difference here that I can sort of see in the following sense. As we said, the L1 regularization tends to push the weights to 0, to be exactly 0, whether L2 regularization just tends to push the weights down to have a small value. Okay, so here what I can see, right, as a high-level interpretation of the difference between these two regularization is that here the network, of course, this network, it's a ReLU activation, right? You can see very well that this is a linear network with a ReLU activation. You can see that the L1 regularization will cause more dead neurons, right? So you will cause more neurons that have no output because all the outputs have weight exactly 0. So you see that this network has fewer transitions in the ReLU because of these 10 neurons, while this function has more transition in the ReLU, right? And you see this in this interval here, let's say between 1 and 3. You see that this network has 1, 2, 3 transition, while this network has 1, 2 transition, okay? So high-level interpretation of the difference between these two penalties. So the regularization by L1 norm, it's usually called lasso regularization, and it's just a name for the guy. Good. Let's look at early stopping. So if you have done some training, then you have seen this curve many times. So the idea is that when you when you do the training, right? So the loss in training is always decreasing, but the validation loss usually has this U-shaped behavior, right? This convex behavior. And the idea is that if you had access, right, to the evaluation over some sort of validation set, then you might choose to save your computational resources and stop the training when you reach the minimum of your validation. Okay, so the idea is that you terminate while the validation set performance is better, right? And sometimes you're not sure what your minimum is. So what you do is that you add a patience parameter. So you decide that you're going to wait 5 epochs to decide whether to stop, and depending on the length of your total epoch, the total number of epochs that you have, you can set your patient to, let's say, 10 or 20, some ballpark number like this. And what you're doing is that you're evaluating your performance on the validation set, and you are deciding, right, if you have passed the point in which you observe a minimum validation set. Of course, this comes with the usual trade-off that we know. So if we use the validation set to get a very good stopping time, then we know that we are sacrificing data that otherwise we will be using for training, and so on and so forth. Very good. So the idea is that when you execute one round of learning, the performance is not as smooth, and you often see all these jumps. So what you're trying to do is that you are trying to decide what is the minimum of your validation accuracy over this sort of noisy behavior of the accuracy. So it makes sense for you to sort of take an average of the past epochs and decide on the average of the accuracy that you see if there was an improvement or not, and then you decide to stop or not. And of course, this is the role of the patients, right? It gives you a larger window to account for the random, let's say the random jumps in the validation accuracy. Okay, so of course the Keras is, some people like Keras, some people like PyTorch, but basically there is an early stop, and you have all the parameters there. And of course, you just ask your copilot to help you in setting these values and understanding these parameters. Okay, you can do some exercises on early stopping. And of course, early stopping is crucial if you are doing a very large training, right? Because computational resources are always critical, right? So you really want to avoid wasting time and resources doing training when training doesn't bring any improvement. Very good. Any questions so far? Let's see if there's anybody in chat. Any questions? Good. Okay, so this was regularization part A. Now we can do regularization part B. Let me go to regularization part B. You can ask any question in chat in the meanwhile. You are welcome to ask. And the storm here continues. Regularization part B. Okay, let's do in presentation mode. Full screen, and then I share again. I share the window. I guess it's always, oh, here we go. Very good. Okay, so we keep discussing about regularization, data augmentation, and dropout. So we did early stopping. That was very easy to understand. No particular discussion there, and then we can discuss data augmentation. Okay. So data augmentation is something that often you do in terms as an algorithm designer, because you want to do the following. you have a small amount of data, and you know that some aspect of your data, they are not crucial to the training process. So for example, let's say that you're doing some facial recognition and you have a frontal view of the face. Of course, you know that your algorithm should be resilient to some set of transformation of your input data. For example, if you change the hue, if you rotate the picture, if it's partially blurred. So you know that your network should be resilient to a set of transformation of the data, and that you as a designer recognize as being inherent in the way in which data is recorded. Okay, so if this picture was taken with a different camera, under different light condition, under a different orientation of the camera, then this should not change the performance of the network. In order to teach the network, right, what are the crucial aspects of the data and what are the aspects of the data that are just incidental, what you can do is that you can take your data, and when you perform SGD, you do some sort of transformation before feeding into your optimizer, and you hope that by repeating this set of transformation randomly through your batches and through your epochs, then eventually what's going to happen is that the network is going to learn to be resilient to these transformations. Okay. So if you're done some CIFAR, then you already seen this part of the code. So you see here that, for example, when you do this data, so here you have a batch, you have a picture, and you already see the APIs that do this, right? So you can do a rescale, you can do a shift, you can do a rotation, and this is all already in the function that does the retrieval of the data sets. Okay. So just remember that not all, you have to be mindful of how you choose your transformation. This is a classical example from MNIST that says, of course, be careful that the 180 rotation or vertical or horizontal flips, they do change the nature of the data in some cases, right? So in this case, you have a 6 that becomes a 9, right? So in that sense, Chinese characters, they are less redundant, right? Because even if you do this type of transformation with the Chinese characters, nothing changes, right? Very good. Of course, this data transformation makes sense on some set of data, and so on some other set of data doesn't make sense. For example, if you have some categorical variable, let's say that you have someone's job, it doesn't matter to perturb someone's job, right? So if you're a student or an employee, it doesn't make sense to perturb that type of data. So always be careful, always be mindful of the type of transformation that you do. Now, dropout. Dropout is very, very important. So let's go back to our original problem that we always have, especially with neural network. And the problem that we have with neural network is always that of overfitting. Why? Because neural network inherently, they are over-parameterized. So the risk that a neural network overfits is it's very high because the number of parameters is so large. Okay. So how do we define overfitting, right? Basically, there are many, as we said, it's a term that it's kind of general, right? We can use it to describe many different phenomena. But basically, the idea is that there is an aspect of the network that memorizes the data instead of memorizing the pattern in the data, and this means that a small change in the training set will result in a large change in the learned network. So the idea is that if you want to prevent this, one way of doing this is by choosing small weights, right? Forcing the weights to be small. And if you choose the weights to be small, in a sense, you forcibly insert another idea of compactness, of minimality of the network, right? So you reduce the expressivity of the network, and by reducing the expressivity of the network, you sort of combat the over-parameterization of the network. And this is one approach to do this. But we know from the machine learning course of last semester that a better way to do this would be to have a pool of network, right? So if instead of having a prediction with one network, we will have 10 smaller networks. We know that the 10 smaller networks, they will tend to overfit less than a single large network. Okay. So this is a different ways of seeing this. So there is the idea that you want to have a pool of experts, right? And you want the pool of experts to be, you want each expert to have a small network so that it doesn't over-parameterize. And then you want to have a pool of network and you want to, let's say, decide the inference by, let's say, averaging the decision of the single independent networks. So again, so this is a concept that we see in the machine learning class. So how can we obtain this in neural network? Okay. So the idea is that somebody will give you this large standard neural network and you want to create a pool of smaller networks. So what you could do in a way which is computationally efficient is to simply switch out some of the networks, some of the neurons, right? So let's say you randomly subsample your neurons, and let's say you just choose 30% of the neurons, and you apply backpropagation to only 30% of the neurons, and you, let's say you train the subnetworks all independently. Okay. So how would we do this in practice? Well, it will be sort of algorithmically complex to really produce a large number of subnetworks, because in a sense we will lose, let's say, we will lose the fact that during inference is very efficient because we can parallelize many operations, right? So we do not really want to construct many independent networks with some random geometry. We would just like to sort of train the network to behave as if there are many different subnetworks that they live inside here, and then you would like to, during inference, to maintain the computational efficiency of having just one big network with multiple layers and some efficient way of computing the activations. So the idea is that the trade-off between these two wishes and wants is to do dropout. So the idea is as follows. So you're given a mini batch, you want to perform SGD, but what you do is that you first select a randomly binary mask, right? And this mask decides which of the neurons are going to be active and which of the neurons are going to be shut down. Then when you do the gradient update, you apply the gradient update only on those nodes which have not been dropped out, right? So dropout, let's say the dropout means that the associated variable is set to 0. If the associated variable is not set to 0, then you are an active neuron. And so the idea is that you will apply the gradient step, you will apply the model update only for the neurons that have not been dropped out. So this actually works, and it works very well, and it does prevent overfitting in some substantial manner. And the idea is that you choose, let's say, something as follows, right? So the input nodes are active with certain probability, let's say 0.8, but usually you don't really touch the input neurons. Usually you let the input neurons be all active. But then for the hidden neurons, you choose a dropout probability of somewhere between 0.5 and 0.3, right? So you decide that the half of the neurons or a third of the neurons are active at that point in time. And incredibly, right, as many things in machine learning, this technique works, and it works very well, and it's very efficient, and it's very much used. And you see here the performance. So here, this is the number of weight updates. So these are the epochs. This is the accuracy, and you see that indeed when you are dropout, you have a large gap in the accuracy. Okay, so these are the various iterations of SGD, and in one you do dropout, and the other you don't, and you do see that this is actually what happens, right? That if you do dropout, you do really teach the network to have some very predictive, some very powerful subnetworks that just emerge from this random ensemble of network that you have generated. Okay, and this is what we call dropout. And then the question is, what happens at inference time? At inference time, then you do not perform dropout. So at inference time, everybody is aggregated, right? All the networks are aggregated, but of course you have to add some weighting probability, which is some weighting to the updates, and the weighting corresponds to the probability of the node being active or not, right? So let's say you train this network, and this neuron was active with probability P. Then during test time, you update the weights as not omega, but as P times omega, right? So you multiply the weights by the probability that the neuron was active. Okay, so remember that you have to regularize things as follows. Very good. Of course, depending on your activation function, you might or you might not need to do this, right? But in general, remember that this is the idea. Okay, very good. That's it. So let's see if we can do another set of slides. Any questions you ask me in chat? And then we can do batch normalization. It's very important. Batch normalization. Any questions, you let me know. Let's see, let me share the screen again. I wish there was something more efficient to, for sharing a large set of slides. Okay, good. So batch normalization, another very important technique in training. So the idea is that when we do inference, usually we always normalize the features. Okay, that's because we do not have any good reason, right, to imagine that some of the features should have a different range than other features. So usually we would like to have some uniformity in the weight distribution. So if we normalize the features, then we know that also the weights will usually behave in a nice way. Okay. And you can do this test by yourself. Just try to train the CIFAR dataset and remove the normalization of the features, and you will see that a mess happens, right? Or what you can do is that you can normalize some of the features and do not normalize other features, always in the CIFAR dataset, and you will see that it's a mess, right? So the performance usually is always increased when you have a nice normalization of the data. And what is the interpretation that you have? Let's say that you can say that if the features were not normalized, right, then the sensitivity of the loss function to the range of the different features will be such that you'll introduce, let's say, some skewness in the weight distribution. Okay? The weights that are connected to some features with a large range will have a certain distribution, and the features connected, the weights connected to features with a smaller range will have a smaller distribution. So this will give rise to this sort of ellipsis, right? So this will be the set of omega of the one feature. This is the set of omega of the other features. You will have this sort of skewness of the weight distribution. But the idea is that if you normalize everything, then you have, let's say, a more regular, a more symmetric, let's say, distribution of your loss with respect to the weights. So the sensitivity, the sensitivity of the loss function with respect to each feature is sort of uniform. Very good. So if you apply this type of concept, not for the input, but for the hidden layers, then you have an interesting idea to think about. Okay, so the idea is that as you go down to the layers of the network, of course, what happens is that if you consider this layer to be the input layer for the rest of the network, then you will also want that the output of the previous layer will be normalized. And if you have a nice behavior by normalizing the inputs, why wouldn't you have a nice behavior by normalizing the intermediate features from layer I to layer I plus 1? Okay, so this is where let's say the core of the idea of batch normalization comes from. Okay, so the idea is that if you could do this normalization, right, maybe you will have a faster learn. Okay, because again, we will have that all these intermediate features, they will have a better horizon for the optimization, so the optimization will be faster. Good, good. Okay, but where do we do the normalization? Okay, of course, we have to do it mini batch wise, because when we do the calculation of the activation function, we always operate over mini batch. You know, one of the dimension will always be the mini batch dimension. Okay, so the idea, if this is your the features transmitted from one layer to the other one, then you will have n mini batch points. You see that the first index in the mini batch point, and the other index will be the neuron output from one layer to the next layer. So let's say that we have k hidden units, then this will be the output of layer 0 to layer 1. This will be layer 1 to layer 2, all the way to layer k minus 1 to layer k. So the idea is that the representation, right, of the inference of the network will always be in terms of mini batch. Okay, so this is the data representation. So what you want to do actually is to take one of the rows here, right? So you will want to look at all the input-output relationships from one neuron to from one layer to the next over a mini batch and normalize over the mini batch. No problem. And the normalization that we do, it's always this sort of second-order normalization. That is, we imagine the data to be Gaussian. So if we remove the bias and we normalize by the variance, then we have a Gaussian-like distribution. Okay, so the Gaussian distribution only has two moments. It has the mean and the variance. It has the mu and the sigma, and these are this is the normalization for the moment that there is interest of us. Okay, so what we want to do is that we want to take the data in each batch, subtract the empirical mean of the batch. So we sum all the elements in the batch and see what is the mean of the batch. And then we want to look at the variance of the batch. So what we do is that we take the element in the batch, we subtract the mean, and then we square and we sum them up. Okay, so this is the empirical mean, and this is the empirical batch of the variance, and we will want that the input-output from one layer to the next are normalized in terms of mean and variance. Okay, so many things for you to think about here, of course. So the idea is why do we stop at first and second moment, right? So of course, what we're doing here is that we are setting the first moment to be 0, the second moment to be 0. So the question that you ask yourself is, well, why don't we put the third moment and the fourth moment to be 0, right? If you want to inject some regularity in the training, why do we only do this for the first two moments, right? Well, one answer for you is that there is also, of course, a complexity consideration. So you can imagine that taking these squares as a certain complexity. So if you take something larger, if you take a power 3, you take a cube, then you're going to increase the complexity of this normalization. And then there is also a consideration with respect to the value of higher moments. So for example, in the challenge this week, you saw the difference between first order optimization and second order optimization. So you see that pushing for higher order normalization doesn't really buy you so much. It's not that higher order always mean better. And this is sort of another consideration of this type, right? So we have a certain experience with these algorithms, and we understand that normalizing this sort of Gaussian normalization, this setting the first moment to be 0 and the second moment to be 1, it is generally sufficient for us to have good performance. Okay, good. So the idea is that then during inference, right, what's going to happen to these parameters? So the idea is that you want to have learnable parameters for the mean and the variance, right? So you want to say that your normalized input-output relationship between layers, it's learnable in the sense that you have a multiplication and a shift that are learnable parameters. Okay, so basically you will set up a problem in which this the network decides sort of a normalization constant, right? These multiplicative and additive constants that control how the input-output of each layer is normalized before being passed on. Okay, so the idea is as follows: is that you have n batches. For each batch, you do the following: you take the inputs in this batch, you normalize them in terms of mean and variance. Then you do this for the n batch, and you repeat this over all the possible batches. You see that here I iterates over the batch from 1 to n, and then this mean and variance, right? They are obtained by empirically averaging over the batch as well. Okay, so for each batch, you have a certain mean and variance. Then this mean and variance, they are all stored, right? And during inference, you will also be learning these parameters. Okay, very good. Then once we've done this, we can repeat this for each layer, and this normalization will be from layer to layer, and then we do this until we have exhausted all our layers. Good. So this is what happens during training. Let's see what happens during inference. And of course, this is what we said, right? That during inference, you will just use a global mean and variance for each layer in terms of normalization. And this will be the averages over all the possible batches. Okay. So the idea is that you store the mean and the standard deviation during training, then you calculate the empirical average of this mean and variance. So you have a mean of mean and a variance of variance. You have a mean of mean and a mean of variance. And this is what you use during inference. Okay? Very good. And you guys know that I don't like to talk too much. Let me see if we can do another set of slides. If you have any questions, meanwhile, let me know. Otherwise, we discuss briefly parameter optimization and then move on. Dun, dun, dun. Screen. View full screen. And then I share. And then I share the window with the. So frustrating, guys. So frustrating. Good. So let's just describe parameter initialization. This is something that you guys are already familiar with, right? So we don't want to spend too much time on this. But the idea is that when you initialize the weight of a network, you would like to initialize it to a good initial point. And what does it mean, a good initial point? Of course, the point has to be random, meaning that if you repeat the training multiple times, you are really exploring all the space of the possible solution for the network. And you want to initialize them in a way which is, of course, not symmetric, right? Because you know that you always run the risk that, for example, if you initialize some weights to 0, then the network never starts learning because all the weights are set to 0. So there is no gradient to be computed initially. So of course, random initialization is the best choice. And the idea is that people like to choose a few distribution for the initialization. Usually it's Gaussian or uniform. And this choice is, again, comes from experience and also comes from some sort of complexity consideration, right? So generating a random variable, it's not always easy. And the random variables that we can generate easily are the continuous uniform distribution and the Gaussian distribution. If you give me another random variable to generate, the generation generally is not easy. Okay, so for the continuous uniform distribution, it's clear what you want to do, because if you the basic random operation that you have in the computer, it's the pseudo-random generation. So you can generate very good sequences of zeros and ones that looks as if the bits are IID 0.5, uniform IID. So what you can do is that you can just take a string of length, let's say 32, and if you take a binary string between 0 and 32, and you add a dot at the beginning, then you have a number between 0 and 1. So if the sequence is randomly uniform in terms of bits, then it will be randomly uniform between 0 and 1 as a continuous random variable. So you will have a uniform continuous random variable between 0 and 1. In order to do the Gaussian distribution, I can let you think about it a little bit, but it's funny. So there is a very easy transformation to bring uniform distribution to a Gaussian distribution. Let me actually ask in chat. Do you know how to easily build a Gaussian distribution from uniform random variable? Random variables. Because so you guys don't see much of this type of algorithms, and I think the algorithm that you guys know must be the inverse CDF algorithm. That's it. So in the inverse CDF algorithm, you basically take the CDF of a function, and you take a random variable between 0 and 1, you place the CDF, and then the inverse mapping from the 0-1 interval back to the point on R will give a random variable which has the same distribution as the random variable whose CDF you used. Yeah, let's see if anybody has any idea. It's a good exercise. So I'll tell you the trick, since you are here when you should be in vacation. So the issue, of course, do you know the inverse CDF method would generate random variables? Question mark 0/1. Come on, guys. Just few of us. Okay, good. One guy knows. Let me just show you quickly so that we are on the same random variables. We're on the same page. This one here. Let's see this one here. I think this is a good plot. So the idea is as follows, right? So let's say that you have a CDF. So the CDF will go between R and 0.1. So this is a one-dimensional random variable. So what you do is that you draw the CDF. The CDF, let's say, will go between -infinity and +infinity. And on the x-axis. And on the y-axis, it will always go between 0 and 1. Because when you integrate the CDF, you're going to get to 1, +infinity. So what you do is that you take the interval between 0 and 1 here, you draw a uniform random variable. Let's say that the uniform random variable of false here. Then what you do is that you trace back which value of the y will map to that point of the CDF, and this will produce a random variable which is distributed according to the y distribution, which is the one that gives the PDF. The proof is very simple and very elegant, right? Because the probability that x is smaller than x is the probability that the point is below the uniform distribution in the u in the 0-1 interval, and so the CDF of the variable that you generate in this manner, it's the same as the desired one. Okay? So it's very elegant, very nice, very cool method. But again, this is computationally efficient only when your CDF has a closed form distribution. Because if you don't have a closed form expression, then numerically inverting the CDF could be very, very expensive. So in general, this is where the computational complexity of generating a random variable is. It's in finding this inverse of the CDF. And then crucially, like, it doesn't work for a higher dimension. So if you want to do this in higher dimension, then the complexity explodes. And the idea is that the Gaussian random variable, what happens is that if you take two Gaussian random variables and then you switch to polar coordinates, right, then the phase is going to become uniform and the amplitude is going to become Rayleigh, right? And what is the beauty of the Rayleigh distribution? The beauty of the Rayleigh distribution is that the CDF, it's computationally very easy, right? It's just e to the minus something. So when you want to generate a bunch of Gaussian random variable, that's what you do. You generate a uniform distribution that will become the phase. You generate a Rayleigh distribution using the inverse CDF method. Then you will change from polar coordinates to Gaussian to Euclidean coordinates, and from those two uniform random variables to uniform random variables, you get two Gaussian random variables. Okay, so this is the trick that makes it the computation of the Gaussian very efficient. Okay. If somebody, of course, if somebody tells you that they want a distribution for the weights, which is some very exotic distribution, some beta distribution with 5 different parameters, of course, this can be done, but it's not computationally efficient. So if you have to do many initialization for many networks, for many learning problems, then this will be a limit to the complexity. Of course, everything is relative, right? So if you're doing 2 million epochs, then the cost of initialization is not so high. So everything, everything has a trade. Anyway, so that's why we use the Gaussian and the uniform. And what do we do with this information? We want to choose sort of what is the range, what is the variance of our random initialization. Because if we have a very large variance in our initialization, then we're gonna explore a larger set of the network solution, right? We're gonna start from many different possible networks so that we have a better choice of landing on a good local optima. And if we choose a smaller variance, then the training is more stable. So we're gonna have a more smooth training, less jumps during SGD. What is the other side of the coin of this, right? So if we choose very large initial weights, then it's very easy for the gradient to explode. Okay, so you might have experienced gradient explosion yourself sometimes. So what happens is that since the gradients are multiplied from layer to layer, from the bottom to the top, if the gradients are increasing from layer to layer, then this will create a sort of cascade effect where across iteration, then the gradients tend to explode. And the other side of the coin of this that you might also have experienced is that vanishing gradients, right? So basically, if the gradients are very close to zero, multiplying the gradient from layer to layer will bring the solution to be zero. So in a sense, you are trying to trade off between these 4 effects, right? Large variance, small variance, large gradients, small gradients, and you want to, let's say, find a meaningful trade-off in your initialization. What people usually do, what is the standard in, let's say, Torch or Keras, is to choose the weights to be Gaussian 0, 1 over m, when m is the number of inputs. And then if you have a ReLU, then you recommend what you usually take is 2 over m. Okay, so something to experiment with in terms of solution. Very good. And then you always have fully connected layer versus convolutional layers. So we know that convolutional layers tend to be much sparser than dense layers. So if you have m inputs and n outputs, then usually you take this uniform distribution with this type of range, right? And there are many heuristics that people have come up with, different distributions to promote different levels of sparsity. Yeah. It's something that people have researched for a long time. So this is the initialization of the weights. What about the bias? So the idea is that you don't want to have the bias exactly equal to 0, because we don't like zeros, because multiplied by 0 kills the gradient wherever the gradient was coming in. So you want to have a bias which is at least an epsilon away from 0. And then you can try to match the statistic of the output of the training set, right? So you can try to have a bias that will match for example, the mean of your input distribution. Yeah, of course, you want to avoid dead neurons, right? So for the ReLU, you always try to initialize them away from 0 or in the positive range of the ReLU, so that you don't start with all neurons being dead. Okay, here you see some example with of the different learning performance with different initialization, right? So you see here that if the range is smaller, let's say, then the network is sort of smoother, right? So you tend to land on networks with smaller weights that have a smoother behavior. If you choose a larger initialization, then you end up more extreme network that have larger changes. So there are many stories that we can tell ourselves on how to interpret the relevance of this. Very good. Okay, good. I think that's it for today. We covered 1 hour. You know that, yeah, I don't like to talk too much. So any questions so far? So logistically, we are gonna release the new groups. So because next week is the midterm week, so we know that you guys are gonna be busy. So we're gonna choose much simpler challenge for challenge 4. We're gonna release the groups in time this time. We're before Friday, and then submission of the challenge will be this Friday. So when you present next week, that should be the midterm week. Should just be presentation. There should be nothing to do. And then the challenge, basically, we understand that you will do it in the week after the midterm week. So that's why we choose it very simple. Nothing to be afraid of. Okay. Anything else, guys? Otherwise, we stop recording and we see each other next time. Okay, I'm gonna stop the recording. So if you want to ask something away from the recording, is there? Hi to the people at home.